next lesson in our reactions in stoichiometry unit is the last essential standard for the unit, 5.1b, on basic stoichiometry. So that word stoichiometry, I know, is not one we are familiar with, and you can see our success criteria here. That first success criterion, I can define stoichiometry, will give you a definition, and you will see exactly what that means. It's really quite simple, the idea of stoichiometry. So we want to be able to define it and explain how moles are related in a reaction, and then we want to be able to convert between mass, moles, and particles to determine quantities in a reaction. So let's just jump right in here and see what this whole idea of stoichiometry is. So what is stoichiometry? If you want a textbook definition, you might see something like this. It is the it is the quantitative relationship between moles and thus mass and particles of the reactants and products in a reaction. So the question becomes, where do we get these quantitative relationships between moles? This mole relationship is given by the stoichiometric coefficients in a balanced chemical equation. And note the emphasis there on the balanced chemical equation part. If the equation is not balanced, we cannot do stoichiometry. This term here, stoichiometric coefficients, those are those same coefficients that you use to balance an equation that you've already learned about. So for example, this is the first equation I believe we looked at balancing the formation of water, where we said we needed 2 molecules of hydrogen to react with 1 molecule of oxygen to give us 2 molecules of water. Well, as far as stoichiometry is concerned, these coefficients, the 2, the 1, and the 2, and do remember if there's no coefficient there, it's understood to be 1, those are mole ratios, number of moles. So what these stoichiometric coefficients tell us is that 2 moles of H2, 2 moles of hydrogen, will react with 1 mole of oxygen, the O2, to produce 2 moles of water. So when we say stoichiometric ratio or stoichiometric coefficients, all we're referring to are the coefficients of the balanced equation, and those give us a mole ratio. So for every 2 moles of hydrogen that react, 1 mole of oxygen has to react, and we'll get 2 moles of water. In other words, we could write those as equalities, where 2 moles of hydrogen equals 1 mole of oxygen, which equals 2 moles of water. Because we can write them as equalities, we can use those as conversion factors, which will become a very key point for us as we look at these example problems. So a basic stoichiometry question, and this one here won't even require any significant calculation, we'll be able to do it in our head. How many moles of water are produced if 5 moles of oxygen of O2 react? Well, thinking about what these ratios, these stoichiometric coefficients tell us, for every 1 mole of oxygen that reacts, we will get 2 moles of water. So it's a 1 to 2 ratio, 1 mole of oxygen for 2 moles of water. So if 5 moles of oxygen react, if I had 5 moles of the oxygen, I'm going to get 2 moles of water for every 1 mole of oxygen. So if it's 5 moles of oxygen, I will get 10 moles of water. So 2 moles of water are produced for every 1 mole of oxygen that reacts, so 10 moles of water form, because it's that 2 to 1 ratio. So let's look at how we use this idea of mole-to-mole ratios in a more traditional stoichiometry calculation. So let's say we are given this problem. So we're dealing with the same reaction. Consider the reaction between hydrogen and oxygen to form water. And do notice the equation is given to us, and it is already balanced here. If you don't have a balanced equation, you need to balance it in order to be able to answer these questions. So the question is, if 2.5 grams of water are produced, what mass of oxygen reacted? Now recognize that this question is not asking us about moles, but because we are relating an amount, whether it be mass, moles, particles, of one substance in a reaction to another, we will need to use a mole-to-mole ratio. But we have to convert it to moles first. So ultimately what we're asked to find here, how many grams of oxygen, what mass of oxygen reacted? So I'm looking for grams of O2. If 2.5 grams of water are produced. That's where we're going to start with our problem. Now I need to convert this to moles because I need to use these stoichiometric coefficients 2 to 1 to 2 in order to do this conversion from water to oxygen. So the first thing we're going to do is we're going to convert from mass of water to moles of water. So this is just a mass to moles conversion, which we've been doing for quite some time, just using the molar mass of water, 18.02 grams of water for every mole of water, where grams of water cancel, and we're left with moles of water. Now that we have moles of water, now we can use the mole to mole ratio in the balanced equation. I look at my equation, I can see 2 moles of water are formed. That's what the stoichiometry, the coefficient 2 tells me, for every 1 mole of oxygen. And again, I will emphasize that there is no coefficient there. It is 1. It doesn't mean 0. It's 1. So for every 2 moles of water, and notice where my units go to cancel, moles of water has to go in the denominator to cancel with this moles of water. For every 2 moles of water that are formed, I react 1 mole of oxygen to get there. So notice moles of water cancel. Now that I'm in moles of oxygen, now I can convert from moles of oxygen into the unit we're looking for, grams of oxygen. So that's just another mole to gram conversion using the molar mass. And do recognize it is O2, it's diatomic, so it's 32 grams per mole, not 16. So moles of O2 cancel. We get that in the numerator here, denominator here. And now notice my units work to give me the grams of oxygen, which is what I'm looking for. If you plug that into your calculator, round for significant figures, you'll get 2.22 grams of O2. One note on sig figs, this mole ratio that we use here, this 1 to 2, it is exact. We don't have to measure that. It's not going to be 1.98 moles of water reacting for every 1.003 moles of oxygen. It's exactly 2 to 1. So there are an unlimited number of sig figs there. What's limiting our sig figs in this calculation is the initial mass of water. 3 sig figs there, so our answer will have 3 sig figs. Here's the big takeaway from this entire video. All stoichiometry calculations, so anytime we're asked to compare the amount of one substance in reaction to another, they always require the use of a mole-to-mole ratio from the balanced chemical equation. And notice I use that right here, where these numbers, this 1 mole of oxygen for every 2 moles of water, come from the balanced chemical equation. You can see the 1 mole of oxygen here, 2 moles of water here. Every stoichiometry problem, regardless of what you're asked, will always have to use a mole-to-mole ratio or mole-to-mole conversion in there somewhere. So let's keep that in mind as we work through these other examples. All right, first question. Magnesium and hydrochloric acid produce magnesium chloride and hydrogen gas. You can see I give you the equation there. What mass of magnesium is needed to produce 0.015 moles of hydrogen? Recognize this. Remember, the first thing that we need in order to do any of these problems is a balanced chemical equation. So ask yourself, is this equation balanced? The answer is no. You can see on the left side we have 1 hydrogen atom and 1 chlorine atom, but on the right we have 2 of each. So the first thing we have to do is we must balance the equation. If I simply give you an equation on a quiz or a worksheet or something and you don't see coefficients there, assume that it's not balanced. Go back, check it, get it balanced. So in this case, we need a 2 there in front of the HCl in order to get this balance. That'll give us 2 hydrogen atoms and 2 chlorine atoms on each side of the equation. You can see the 2 there to get it balanced. All right, so the question ultimately asks us what mass of magnesium, so how many grams of magnesium, are needed to produce 0.015 moles of hydrogen. So how many grams of magnesium equal 0.015 moles of H2? Recognize the difference in this problem compared to the one we did before. Oftentimes students will automatically use a molar mass here to convert from moles to grams, but I don't need to know how many grams of hydrogen that is. I just need to get to magnesium. So because we're starting with moles here right away, I can use the mole-to-mole ratio in the balanced equation. So I look up at my balanced equation, I have 1 mole of magnesium for every 1 mole of hydrogen. And again, we're looking at those balanced stoichiometric coefficients, 1, 2, 1, 1. So 1 mole of magnesium for 1 mole of hydrogen. Notice moles of H2 cancel. Now we have moles of magnesium. Now we can convert from moles of magnesium to grams of magnesium, just using the molar mass. Molar mass of magnesium from your periodic table, 24.31 grams per mole. Moles cancel, and we have our answer. And again, recognize your sig figs. These 1s here It's exact. It's exactly 1 mole of magnesium for 1 mole of hydrogen. So those don't limit our sig figs. In this case, the 0.015 moles of hydrogen, 2 sig figs. So our answer has 2 sig figs. All right, another question dealing with the same reaction. What mass of hydrochloric acid is required to completely react with 1.2 grams of magnesium? One thing that students will tell me they struggle with in this is, on this particular question is, well, Mr. Kurtz, I don't know what hydrochloric acid is. Well, just go back and consult the equation, okay? If nothing else, use process of elimination. Now, yes, we should be able to write out that formula, but even if you're not sure how to do that, you can figure it out by looking at the equation here. Well, I know that's not hydrochloric acid because just magnesium, and that's magnesium chloride, and that's just hydrogen, so geez, that must be hydrochloric acid there then. So just use process of elimination if you're not sure. So we're asked to find the mass of hydrochloric acid, HCl, that is required to completely react with the 1.2 grams of magnesium. So how many grams of HCl equal 1.2 grams of magnesium? So just a conversion like we did before. Remember, we have to get it to moles first. Now, on the previous example, we were already in moles, so we just did our mole-to-mole ratio for our first conversion. But here, we need to get it to moles first because we're starting in grams. So use your molar mass to go from grams to moles. Notice grams of magnesium cancel. Now I can use my mole-to-mole ratio. Again, this here comes from the balanced chemical equation. Look at my equation, 1 mole of magnesium for 2 moles of hydrochloric acid, so moles of magnesium cancel. And now I have moles of hydrochloric acid, HCl. I can go from moles of HCl to grams of HCl using the molar mass. So just look at your periodic table, get that calculated. That's 36.46. Moles of HCl cancel, and we can get our answer. Again, notice the 2 sig figs there. That initial mass is limiting us. This last problem and the one from the previous slide sometimes will be referred to as gram, mole, mole, gram problems, and you'll see why here, because we start with a mass in grams, we convert it to moles, we convert it to moles, and then we convert it to grams. This is by far the most common stoichiometry problem, simply because that's what you measure in the lab. You measure masses. We can't really measure moles directly. We have to measure out masses. And so this gram, mole, mole, gram conversion is one that we do almost every time. Yes, not all the time, because the previous example we can see we actually started with moles. But this here, from grams to moles to moles to grams, is a very common situation to have to do in chemistry. All right, one more example, then I have a couple for you to practice on your own here. So aluminum chloride and sodium hydroxide react as follows. What mass of aluminum hydroxide can be produced if 0.287 grams of sodium hydroxide react? Again, recognize I have given you the equation, but you don't see any coefficients there, so assume that it is not balanced yet. Now, yes, it is possible that an equation is balanced with all ones for coefficients, but if you don't see any there, assume that it's not balanced. And so we must have a balanced equation first. And looking at this, I can say I have 1 aluminum on each side, so that's good. 3 chlorines on the left, only 1 on the right. And then I have 1 sodium, 1 hydroxide ion, and 3 hydroxide ions on the right. So a couple things there aren't balanced. So to get this thing balanced, we'll have 3 moles of sodium hydroxide. That'll give me 3 atoms of sodium on the left. And it'll give me 3 hydroxide ions, which will balance with those 3 on the right. And then if I have 3 moles of sodium chloride, now I have 3 chlorine atoms on each side. You can see that there. And 3 sodium atoms on each side. So it's balanced. All right. So the question, what mass of aluminum hydroxide, AlOH3, and again, if you need to, just consult the equation for helping you write these formulas. If you're not sure what the formula for aluminum hydroxide is, just go back and pick it out of the equation, and you should be able to figure it out pretty easily from there. And I want to know what mass of that can be produced if this 0.287 grams of sodium hydroxide react. So notice this is just a gram, mole, mole, gram problem. Starting in grams, ending in grams, but I need to convert between the substances using the mole ratio. So going from grams to moles using the molar mass of sodium hydroxide, that's 40.00. Notice your grams of sodium hydroxide cancel, and that leaves us with moles. Now I can use my mole ratio. 3 moles of sodium hydroxide, again right from the chemical equation, for every 1 mole of aluminum hydroxide, the AlOH3. Moles of sodium hydroxide cancel. Now I can convert from moles of aluminum hydroxide into grams using the molar mass, again just calculated from your periodic table. Moles cancel, and I'm left with grams of aluminum hydroxide. I get an answer. It looks like 3 sig figs here. My initial mass is limiting us, so 0.187 grams of aluminum hydroxide. All right, a couple of problems here for you to practice. Once I present the problem, pause the video, try it yourself, and then play it and see if your work matches mine. All right, so here's the first question. Consider the decomposition of trinitrotoluene, which sometimes is abbreviated TNT. So this here is the formula for trinitrotoluene, the C7H5N3O6. And you'll notice you already see stoichiometric coefficients there. So that tells you I've balanced it for you already. I'm not going to intentionally balance it wrong, just so you know, so I'm not going to try to trick you. If you see coefficients already given to you, then assume it's balanced correctly. If I happen to mess up the balancing, then that's not your fault, that's on me. But I would never do that intentionally. So the question is, what mass of carbon monoxide, so find your carbon monoxide, that's right here, what mass of carbon monoxide can be produced if 3.65 grams of TNT decompose? And again, here's your TNT right here, the trinitrotoluene. So instead of writing out this C7H5N3O6 all the time, I think what I did here, I'm just abbreviating it TNT so to make it a little easier to look at. So this is just another gram, mole, mole, gram problem. If you haven't already paused the video and tried it yourself, go ahead and do that. All right, so we're going to convert from grams to moles first, just using the molar mass. Again, that's the molar mass of this right here, the C7H5N3O6. Grams of TNT cancel, going from grams to moles. Now I can use my mole to mole ratio. Notice I have 2 moles of the TNT for every 12 moles of the carbon monoxide, so that's my 12:2 ratio there. Moles of TNT cancel. Now I can convert from moles to grams. Moles of carbon monoxide cancel using the molar mass of the carbon monoxide, and that will give me the 2.70 grams of carbon monoxide. Okay, second question here, dealing with the same reaction. Again, if you haven't already done so, pause the video, try it yourself, and then give it a shot. So the question, how many moles of hydrogen are produced when 100.0 grams of carbon are produced? Notice here, this question is asking us for the number of moles. This actually makes it easier, less conversions to do, because all we need to go is the moles of hydrogen, moles of H2. I don't need to go all the way to grams. Now I still need to convert from grams to moles of carbon. Okay, so using the molar mass of carbon, 12.01 grams of carbon per mole. Grams of carbon cancel. Now, to go from moles of carbon to moles of hydrogen, it's just a mole to mole ratio. Looking at my balanced equation, 2 moles of carbon here for every 5 moles of hydrogen here. So that's what I use in my conversion factor here, 2 to 5. Moles of carbon cancel, and notice that's it. I'm asked to find moles of hydrogen. I'm in moles of hydrogen. A common mistake students will make here is they'll just go ahead and convert it to grams because that's just what they're used to. And what that tells me is, yes, you may understand how to do the gram, mole, mole, gram problems, which is great, very important, but it tells me that we're not really understanding what it is we're asked to find. Okay, where we don't want to get in the habit of just doing the same calculation over and over and over again, because sometimes we're asked for something different. So in this case, just moles of hydrogen, plug that in your calculator. Looks like we get 4 sig figs here, so 20.82 moles of H2. All right, so that concludes the practice and the examples there. So just reviewing our learning goal and success criteria. Our learning goal, I understand how to quantify chemical reactions, and we looked at the 2 success criteria there. I can define stoichiometry and explain how moles are related in a reaction, and I can convert between mass, moles, and particles to determine quantities in a reaction, and you saw examples of all that there.